Okay. All right. Thanks everyone for joining us today. Today we're joined by Chinmay Hegde. He's an associate professor at NYU Tandon in CSE and ECE. He works on a lot of interesting problems, foundational aspects of machine learning, applications to computational imaging, materials design, plant science, and today he's going to be talking about AI-generated content and detection methods for that. He's won a lot of awards, NSF Career, CRII, teaching awards, and best papers at ICML, SPARS, MMLS. So we're really looking forward to hearing more about watermarking. So go ahead.
Can you hear me? Everybody can hear me? Thanks, Akshay, for the kind introduction and the invitation to come here. The first time I'm visiting NJIT, even though I'm across the river. So happy to be here. Just want to also mention that most of the work I'll talk about today is joined with many excellent people, in particular, Neil Cohen, who's my postdoc, and Govind Mitchell, my PhD student. Primarily, I'll be talking about their work. But I want to set up the stage by talking about something that I hope everybody knows already. I don't have to introduce anybody to generative AI. We are in age of marvels, where magical machines answer any question that we ask it, or even compose songs in the style of whoever our favorite artist, or even bring our thoughts to life. Right, so it's an incredible time, and the best part about all this, it's all completely free. There's like so many models out there that you can play with. And right now, if you wanted, you can generate images of your favorite comic book hero or other heroes. Art. In fact, Hugging Face, which is the ecosystem for open source models. If you go and look at any, on any random day, if you go look at what the popular models are, it's primarily a lot of sort of text to image models, right? Where this seems to be really part of the public imagination as of late, where you prompt a model and out pops an image. So this is all great, and we're in an excellent age. It's a joy to live in, but of course there are perils. Many perils, in fact, such as, for example, copyright. So most of these models have been trained on the public internet, and with no regard to IP protections or copyright. And of course, very soon after these models came out, they started being sued by the owners of the IP. So Getty Images, one of the popular image hosting websites, sued Stable Diffusion because what the model reproduced was exactly the same as one of their photographs. But also artwork, right? So people spend decades honing their craft, and then now comes a model which can exactly mimic how they produce art. So this, of course, also is a major issue, for artists, and also just demographic biases. Many of these models have skewed data sets, and if you ask them to generate, for example, a scientist, they are always of a particular ethnicity, not others. Of course, you can ask why, but we don't have answers to them yet. But definitely there are several issues. That's one set of issues, right? So IP protection, data set bias, and so on. Perhaps a more insidious type of challenge is that of deepfakes. Right. So now we have the ability to mimic the appearance of anybody in the world almost. And you can imagine how these things can go wrong. So on the bottom left, there was a famous incident of, I think about a year ago, of Mark Zuckerberg being interviewed by somebody, and they were talking about how terrible it is for a social media company to take all our data and this and that. And obviously, it was deepfake because the real Mark would never say this. So, but it was so high quality that that was indistinguishable from the real one. So how do we design our models? How do you even envision using these models in the world where such powerful tools exist? In a world where AI-generated content is indistinguishable from real-world content, right? And how in a world where we want to protect both the users of these tools, but also the makers of these tools from various legal issues and so on. So that's what I'm going to spend the remaining half an hour or so on. Talk about methods to detect AI-generated content. Like how do we distinguish truth from fiction, from real from fake? And there are different ways of doing this. There's a whole field in itself. I'll talk about 3 recent papers that we've written in this area. The first 2 papers are on the topic of watermarking, which I'll introduce in a moment. But the last one is on a slightly different active approach for detecting content generated by AI models. Okay, so that's the roadmap, but yeah.
One questions.
Of course.
So like you use our camera, right? Take photo, and that photo will be tuned by some neural network, also like do lightning. Okay.
Sure.
That you treat it as a real or fake?
Great question. Hold that thought for maybe 10 more seconds and we'll have a slide on that. It's a terrific question, yeah. That we'll clarify. Okay, good. Let me start talking about the first paper and then we'll come to exactly that point. And I'll talk about watermarking diffusion model outputs. Maybe a quick show of hands. How many people know anything about watermarking? And how many people know anything about diffusion models? Sort of, okay. All right, so great. I know it's Friday, but I give a mini lecture on both of these things, right? And for the next 2 minutes. Hopefully that's enough to understand what we did. So I'll talk about watermarking first. We all know what watermarks are, right? Like, you've seen something like this, I assume. You have an image and there's like a block of text in the middle of the image saying, something in this image is being watermarked. So that's one example. That's the most common example of watermarking. Coming up to highest point, right? Like, here's a picture. I don't know if you can, and I'm not zoomed in very much, but you can perhaps see this. This is a picture of my kids. It's a collage that you can make in Google Photos if you use Android. And this is made by AI. The AI has made this collage. And you can see on the top right, there's these stars. You've probably seen these stars all over the place. So that is also an example of a watermark, where it's been processed. This particular image is AI generated. And to assure users that this is AI generated, Google places a star on the top. Right? That's another example of a watermark. Actually, the name watermark is interesting. It comes from the medieval ages where people were trying to make paper in Italy, and they left an indistinguishable mark, right? A light mark which made the paper thicker. And if you hold it up to the light, you can see the motif. Right? Again, to assure that this particular media or this particular object had a provenance, right? So that's why watermarks are embedded in certain objects. So, so in the context of images, right, image watermarking, roughly this is the workflow that pretty much all methods, all classical methods pursue. So you have an image. And what we want to do is to watermark this image. So typically, you can either just work with the pixels directly, but what is often done is transform the image into some other domain, like the Fourier-domain, the frequency domain, and then embed a watermark in the frequency domain. Now, why is this done? I mean, typically it's done because we don't want the watermark to be perceptible. We don't want, for example, the giant block. I don't know about you, but I find giant blocks of text obscuring an image somewhat annoying. So ideally, we would like an imperceptible watermark. And this is often achieved by doing the watermarking in the frequency domain. So you now get a watermarked image, which is very similar to the original image. But then we also want to assure that a particular image has been watermarked. So there's always also a detection stage where now if you give me a watermarked image, verifying that it is indeed, it does indeed possess the watermark. So there is a extraction process where you again do the reverse transform and reverse engineer the watermark from the image. And this is physically the same step as taking the piece of paper and holding it to the light. So this is the sort of general workflow for any classical watermarking system, right? And hopefully this makes sense. So what are the properties of a good watermarking system? I would argue that there are 4 desiderata, right? One is its low distortion, meaning that you take an image and I watermark it, I shouldn't change the image too much. I think that makes sense. The second is verification, as we discussed. You give me a watermarked image, I need to make sure that I need to confirm that it's actually being watermarked. Because it's imperceptible, it cannot obviously, it's not a trivial step. So you need to design methods for verification. But there are 2 other requirements for a good watermark. One is that it has to be robust to removal, meaning that, for example, if Stable Diffusion, OpenAI generated an image of Mark Zuckerberg and watermarked it, right? Maybe a malicious adversary who doesn't like OpenAI and shorted the stock shouldn't be able to remove the watermark and then claim that they have deepfaked Mark Zuckerberg, because that will cause lots of issues, right? So it should be robust to removal. It should not be easy to remove. And the reverse is also true. It should be robust to forgery, meaning that if a real image of Mark Zuckerberg existed, it should not be trivial to imprint a watermark on top of it and then claim that, oh, it is actually AI generated and it's fake and so on. So I mean, you can think of these as false positives and false negatives. We want to design watermarks which minimize both types of errors. Does it make sense to folks? So we'll keep the last 2 in mind as we talk about our methods, but hopefully this picture should be clear. So these are the 4 criteria that we want to do. End of mini lecture on watermarking. Okay, so now I'll talk about diffusion models. Again, I talked about generative models where everybody knows about this. You have a long text prompt and you enter the text prompt with as much detail as you want, and then out pops an image. So how does this transformation happen? Like, what are the steps in which these? What are the operations required to achieve this kind of transformation? How does the model function? So for that, we need to unpack the architecture of these kinds of generative models. There are many ways of doing this, but I'll focus on diffusion models for today. It seems like if you go back, it seems like a hard task, right? Like getting this kind of extremely high quality image corresponding to your feature seems like almost like a magical impossible task. At least to me, it did when I first saw these things, right? What is actually very easy is the reverse. This I argue is easy. Assuming that anybody has done any kind of signal processing or any kind of data processing, the process of taking an image and converting to noise is easy, right? Like I just add noise. I sample IID Gaussian noise and add it to my image, and that makes it noisy. And then I sample IID Gaussian noise, add it to this noisy image, it makes it even noisier. So the forward process of taking image and getting noise is trivial, right? I would say it's trivial. Think of like equations. This is the equation. It's just the mathematical way of saying what I just said. Okay, so this is easy to do. If you remember your physics, it's the diffusion equation. Right? You're diffusing, starting with structure and then diffusing the structure everywhere, and Brownian motion is one way to achieve this. Anyway, this forward diffusion process is easy to achieve. Over the years, we have also developed good methods for denoising, meaning let's say that I start with a noisy image on the left and I remove a little bit of noise. Okay. Now you can also believe that this is not too hard. I mean, you can think of your favorite sharpening filter from image processing or other denoisers. There's a whole 50-year-old history of building good denoisers. And I'm not asking for too much. I'm asking for just removing a little bit of noise from a slightly noisy image. So you would also argue, you would agree with me that this is also easy, right? And so in terms of math, it's like if you take the n+1th image in this diffusion process, n+1th step in the diffusion process, I need to hop one to the left. I need to go in reverse, but only one step. Okay. So I need to build an estimator. This estimator depends on the level of the noise of the nth image in the diffusion process, given the n+1th image. Okay, so if you buy the premise that this is also easy, then what is a diffusion model, a generative model which generates these magical images that we just talked about? It's just this denoiser repeated multiple times. So if I gave you if you gave me an oracle which does one-step denoising, I'll give you back a generative model which generates images. And all it does is start with random noise, completely random noise, and apply this oracle multiple times. That's it. Right? So again, diffusion models, mini lecture on diffusion models done. Right? Like, so these are the two things we need to understand. Hopefully this makes sense if you have not seen this before. So now we can start with nothing and get high quality magical images out of it using diffusion models. In this mini lecture, I didn't talk about text prompts, like where does your prompt come in? Right now, there's no control over what you get, right? But there's natural ways to control the output, which we'll come to later. But the key takeaway that I wanted to highlight here is just the fact that you start with noise. An input to this model is noise, is IID Gaussian noise, and then you output an image. And it's an AI generated image. It's a synthetic image. Now my question is, the problem I want to solve is, how do I watermark this kind of image? Like I want to assure any user that this is indeed AI generated and not real. How do I watermark this image? We can apply classical techniques, like the workflow that I just showed. But here's a different idea. This is a sort of idea which is unique to diffusion models, which is that I will watermark not the image, but the noise. Okay. This is specific to diffusion models, right? Like, but because the diffusion model takes noise and gets image, maybe the advantage is to watermarking the noise instead of the image. So if you start with a seed, a random seed, or a random noise vector, I will imprint a watermark on the random noise vector. Right? And that will be the assurance that it is AI generated. Okay, so we can think of like putting a secret key in the noise vector, and that secret key can be used to decode, can be used to assure authenticity later on. So this is the key idea. And in fact, we didn't invent this idea. It is it's been around for at least a couple of years, ever since diffusion models became popular. Perhaps a seminal paper in this line of work is by Tom Goldstein's group at Maryland. It was in Europe a couple of years ago, and they did exactly what I just said, which is that they start with noise, and for specific reasons, they don't watermark the noise directly. They do a Fourier transform and embed the watermark in the domain, and then transform it back. Why is that? Well, Fourier transforms have, if you remember, again, signal processing, they have nice invariances. They have they're shift invariant and to some extent rotation invariant if you do 2D Fourier transforms. And because you want to retain watermarks even if the images are rotated and shifted, that's why you do this watermark in the Fourier-domain. Okay, so hopefully that makes a little bit of sense at least, right? But why is this good? Well, if you now, because I remember it should be robust to removal, right? So if an adversary wanted to remove the watermark by, maybe what they can do is like turn it upside down and say, oh, this is a different image, so no watermark. But actually the watermark persists. So so this kind of procedure is robust to transformations of simple transformations of images, hard to remove. So therefore you can decode the watermark. Okay. So so this method is great. It's robust to perturbations, but not robust to forgery. Remember, we had two requirements, right? Not just that a watermark is hard to remove from a watermark image, but also a watermark is hard to imprint on a real image. And it turns out that this method is not robust to forgery. Okay. So a long-winded way of coming to our contribution in this domain, which is called WIND. And again, we use this idea of watermarking this the noise vector of the diffusion, the noise input to the diffusion model. And in fact, we use the noise itself as a signature, because usually these, if you think of watermarks as secret keys that you embed, well, you can generate a pseudorandom secret key as you would in public key cryptography. And in fact, the noise itself can be viewed as pseudorandom, right? So you can use the noise itself as a signature. So that's a high-level idea. So in detail, we have a particular way to generate the noise, and this is for again cryptographic guarantee reasons. We have a two-stage procedure to sample the noise. It's not a single call to a pseudo-random number generator, but two calls. But once you do that, you can use the randomly generated noise vector as input to your diffusion model and generate the image. Okay. So this is basically the idea. So we do not need to imprint any special key on top of the noise vector as the previous method did. We use the noise vector itself as the key. So this turns out to be both robust to removal as well as robust to forgery. And you can empirically verify this, as we did in our paper. Right? So it at the same time, it's also distortion-free, meaning that it is the same distribution as the original noise, so therefore you get the same kind of outputs as you would if you didn't watermark. So it's distortion-free by design. It's also verifiable because there are good ways of inverting diffusion models. So starting with the image, you can reverse engineer the noise that you started with. And once you reverse engineer the noise, you can check the estimated noise vector with maybe a database of keys that you already had. Questions? I had multiple questions.
Of course, yeah. I asked right. But what if the adversary adds another layer of noise before like verifying it? It's like it's not removing the watermark, but it's basically changed into a different application with the same.
Yeah. In the next slide, I'll show you empirical results where we are robust to those kinds of perturbations. So it is robust to a perturbation attack. Yeah. In fact, I'll show you right now. Here's a slide. It's a big table, but I think the key column to look at is the third column from the right, which is basically noise attacks. So you add noise and try to verify it, and we get 100% verification. Yeah.
Have any predictions for this?
Yeah, let me explain. So again, I mentioned two desiderata, and I claim that our method is robust to both removal and forgery. So what is removal? So I didn't talk about this too much, but there are common ways of removing watermarks. A common attack is take the image and perturb it, and now you cannot detect the watermark anymore. Right, like simple perturbation. For example, if I say this is an image and I turn it upside down, now I can't read that thing anymore. So that in essence, it's been removed. Right, so you can do simple geometric transformations to an image, and these are common attacks for watermarking. And here each column is a different type of transformation. For example, the rotate transformation, you can do something like JPEG compression. You compress the image and then decompress it, and that removes the watermark or makes the watermark obscure. You can do blurring, you can do brightness differences, and so on. And so those are the different columns. Different rows are different watermarking schemes. So I talked about tree-ring before. Ring ID is a sort of slightly better way of implementing tree rings. And the wind methods are different variations or different instantiations of our approach with different parameters. So higher numbers are better. It's a sort of area under the curve for detecting the watermark under these attacks. And as you can see, our numbers are the highest, at least for these kinds of attacks.
Yeah, questions.
Yeah.
What if the attacker gonna be, like apply the same approach for the output of your image, right? They use another, like a diffusions one. They place another watermark or whatever, like there. It's just keep repeating. Like for iterations, a number of iterations, whether your watermark will be destroyed by looping another watermark on top, like multiple times. Have you tried that?
Let me see if I understood the question. So I'm specifically talking about diffusion models.
Can you go back to the other, like, not this, this one, right?
Yeah.
If you generate that image, okay, so you say that is watermark, and you put it on the internet or something.
Uh-huh.
I download it,
yeah,
and then like I apply exactly the same process that you're doing, but I'm gonna repeat it for 100 times. Okay? Because you say that it's all the same, like distribution is distortion-free.
Yeah.
At least it's been like I'm gonna just place multiple watermark, like different one that I have full control, right? To basically manipulate that watermark image, but using the same process that you're doing over there. So at the end, theoretically, like I can still get a very high quality image, but by looping that image multiple times.
Let me see if I understand the loop part. So this is a noise to image generator model. So I'm specifically talking about generator models which look like this. So it takes in noise. It's a generator model like how stable diffusion functions. It takes in noise and produces an image. Maybe you're talking about other types of.
So this one, I put it to a diffusion.
Right.
This is not a conditional generator model.
These are not conditional. Yeah.
So this is not a conditional generator model. So
it's not from the image, but like I can use that image and fit into the diffusion process, right? I get the noise and I fit it. Basically, I feed it to that process again.
Uh-huh.
Yeah, I can do that, right? I block the descriptions from the image to the noise.
Right.
And it's created like a loop like this. Okay?
Right.
I
think I understand. Yeah, you basically apply forward reverse diffusion starting somewhere in the middle of the image.
Yeah, and I look at that, and I just doing the same key or by different key, right?
Yeah.
So logically, it's still in the same distributions, then it's distortion-free. So if I do it well, I still get the very high quality image, but probably like gonna destroy the watermark that you have at the beginning.
So that part, okay. Maybe we can have a chat offline about this. I'm not 100% sure that destroys the watermark because, again, the watermark is the seed which started this process. So even if I understood correctly, the attack that you're proposing right now is a continuation attack in the sense that you apply the diffusion process for many more steps.
Yeah.
Essentially, the thing that we're saying.
Yeah, something like that.
Yeah. So then the verification the defense to your attack will be the same, but in reverse. I will verify it for many more steps. So
there's in addition to that one, we can train the kind of like a segregate model.
Yeah.
So in order to distinguish, okay, this watermark or this not watermark. So I loop the process until I get the image that is not watermark, for example.
Right.
So if you have the API so I can train a segregate model to distinguish them, and then I loop that process like until I get a high quality image, but like it's not one.
Yeah. Okay. So I will. No. Let me say that could perfectly be the case that attack breaks our watermark. It is possible, right? In fact, I'll talk about something along those lines in a moment. Yeah.
The real question would be if I run the same diffusion process and then add another watermark to that. If I run a verifier, would I retrieve both, or would the original watermark be disturbed a bit?
Again, to understand a little bit, so you are adding some kind of key in the middle of the diffusion process.
Yeah. If you added a different.
I have no idea. Yeah. It would be auto distribution. Actually, I'm not even sure if diffusion models would work in that situation. Depends on how you construct the watermark, I think.
Okay.
But not something I've thought of. Okay, assuming that we limit our removals to these kinds of simple transformations, we find that our method is robust. But it's also robust to forgery. So again, how do you forge a watermark? Right? Like, how if I take a real image and I want to pretend that it's AI generated, how do you forge that watermark? The way that typical forgery attacks happen is that you take large numbers of these images. Remember that they're imperceptible, so it's not easy to discern the watermark. But what you can do is sample a large number of images, right, from watermark, a large number of watermarked images, and then do some kind of averaging. Essentially, that's how they work. So if you average out all the features in these images, what you are left with is the watermark. So that's how you reconstruct the watermark. Similarly, you can reconstruct the noise patterns for these models like tree rings, and then recover the secret key. Right? But as I had mentioned earlier, our method explicitly defines against this by doing a two-stage hashing procedure. We don't have a set number of secret keys which we store aside. We generate these secret keys on demand in 2 stages. So that's why it's a 2-stage watermarking process. And in fact, we have a impossibility theorem that under reasonable assumptions of the hash function we use to generate the noise vectors, it's impossible for an adversary to recover this alt. So this again is verified in our experiments. If we attack the tree ring model, most attacks work. It's even a few images, attacks need working, but for our method, you need exponentially many images to forge. Okay, so much about the first approach. I'll maybe speed up a little bit. So I'll talk very briefly about our second approach, and it's still under review. Is a method called SEAL, and the key challenge that we try to address in the second work is, so there's a tension between any watermarking scheme, right? It's like, again, low distortion, but also being able to verify, but also being robust to forgery, right? We have to, so we don't want to distort, meaning that our images should be realistic, meaning that inputs have to be Gaussian. That's how these diffusion models are trained. But then we have to verify. So if we do these kinds of reverse engineering of the noise, it can't be arbitrary, it has to be finite. So the number of keys has to be finite or small, otherwise you cannot verify. But also, at the same time, the keys have to be large enough to fool the attacker. So there's a weird tension that we face when building these kinds of watermarking schemes. And Wind addresses these to some extent. Like it hits the right trade-off of these 3 criteria. But there's a new vulnerability that we discovered while building Wind. My student Teal calls it the cat attack. Here's an image of a nice beach, and it's been watermarked using our method, right? But if I locally tamper this image, say, for example, I add a cat image in the bottom right, local tampering of this image is enough to fool Wind, right? So this is like in fact, the nice table that I showed you earlier is actually, they're all global transformations, like global blur, global noise, global shifts, and so on. But somehow this particular type of attack has not been well studied in the literature, where local tampering actually makes a difference. So how do I prevent these kinds of attacks? We introduce something called SEAL, and here's where text prompting comes in. So remember, again, I sort of hid under the rug the fact that these models not only have a noise input, but also your text prompt. So in some sense, your output has to semantically match what you're trying to generate. So there is a text prompt which produces the image. So the key idea that we use here is to leverage the text prompt. Right? So we make sure that the noise that the pseudorandom number generator that we used to generate the random noise matches the text prompt. Right? So somehow there's some similarity there. Okay. So there's a semantic, the semantics of the prompt is used to guide the noise generation. That's one idea that we use here. That's used in the verification process, as we'll discuss later on. And to prevent these kinds of local attacks from succeeding, we also generate multiple secret keys and not just one. So you can think of images as a bunch of patches. We watermark each patch using a secret key. So therefore, we have local control on what's being watermarked. Yes, question.
To generate random noise too.
Yeah, I'll explain that very briefly. But yeah, I'll explain it in a moment. But yeah, so here's again, I'll show the picture and then maybe walk people through it. So imagine prompt. I want to get an image of a beach at sunset. So that prompt has some semantics. So we can encode the prompt using an embedding model, something like BERT or pick your favorite language model, right? So we get an embedding of the prompt. And now I generate a random key which is close to this embedding. Maybe that answers the question, right? So I generate a bunch of random keys and using something called SimHash, which is a reasonably well-known hashing algorithm, I generate random keys similar to that embedding. Okay, I generate many random keys, as many as patches in the image, and I use those keys to serve as the noise vectors for each patch. Okay, so now then I get a noise a pseudo-random noise pattern, which is semantically close to my original prompt. So that's what I mean here, right? Pass it through the diffusion model, get an image. And it turns out that this is robust to cat attacks, right? It's robust for multiple reasons, but one key reason is that every patch has been watermarked, not just the global patch, right? So you can check whether at patch-wise level, the reverse engineered keys that you estimate are close to the prompt that you provided. And that serves as a sort of natural semantic check. I'll not speak too much more about this, except to encourage people to read the paper. Just also.
It is work the pop-up to watermark the image and release that one else. It have nothing to do with the prompt.
So the purpose is to watermark the image and release it. Release it and make it. Pardon me?
You keep your prompt.
Keep the prompt secret, yeah, exactly.
Keep your prompt secret.
Keep the prompt secret.
But you cannot verify that.
Keep the prompt secret, yeah. So in fact, when I don't know if people can, I'll use my hands to prompt it. So when we do the verification, we optimize the prompt using a captioning model.
Oh.
So the prompt is secret. So your prompt, which you use to generate the image, is secret. I don't need to know it. During verification, I estimate your prompt using captioning. And pass it to the same embedding model and look at closeness of those estimated prompts and your true prompts.
What if I'm trying to fool the captioning?
Yeah.
Right? What if I
being attacked in real time.
Like it's not cat versus a dog?
Yeah.
Your cat attack was the hair turned into a dog. So what are you gonna do with that?
I don't know. Good question. Good question. Yeah.
Perturbations on part of the image and you don't know it. Will this work?
Yeah, this will work. Yeah, this will work. So it has. So let's assume that your perturbations are localized to maybe bottom right patches. In this case, that's the example here. But I apply a perturbation only to the bottom right because I'm checking keys at the patch level. I can detect exactly the patches which are being tampered with. In fact, maybe the picture here might. Here's a picture. I don't know if you can see the picture. The image on the left is a nice image, but tampered with a cat in the middle. And during the verification process, you can see that exactly those patches have been tampered. The patches in the middle. And so simple sort of Euclidean distance tests between the reconstructed noise and your original noise can be used to detect. I don't know if that answers your question. Yeah. Very good questions. But yeah, to to make the point that the method is also robust to removal. I'm running out of time. How much more time do you think we have? Or keep going? Okay. We have one more set of things to talk about. So, all right, I'll just say that this works. It works in a bunch of different cases. But so much about watermarking, right? So I talked about watermarking so far, but I made several assumptions. Not just me, but the field makes several assumptions. The basic assumption is that you assume that the model owner is willing to watermark. Now you can compel the model owner through law. You can compel OpenAI to watermark every image that you generate using OpenAI API or something like that. Fine. But the reality is that there are already very good models which are open source, which you can use to generate whatever you want. I mean, and there's no such thing as watermarking those models. I mean, you cannot watermark Stable Diffusion. It's already public. What do you do with those? With such, I mean, we're already in the world where generative AI is proliferated and cheap and everybody can use it. Like then the whole idea of watermarking those models doesn't make much sense anymore. Right, so the threat of deepfakes is extremely alive, regardless of everything that I just talked about. Yeah, so how do we make sure that Mark Zuckerberg cannot be deepfaked? I mean, we can maybe make sure that cannot be deepfaked using OpenAI models starting today. That can be done using the techniques I just discussed, but not in general. So to address this particular point, I propose doing something else. Everybody has used CAPTCHAs. What are CAPTCHAs? So CAPTCHAs are active challenges that you provide. So you think that something is fake, somebody is fake. You want to ask them to confirm their identity or prove their authenticity. So you issue a challenge to make them prove their authenticity. Right? So that's a traditional CAPTCHA. So now think of somebody in the deepfake setting, somebody maybe doing a Zoom call, maybe it's an interview for a company over a Zoom call, and they're faking somebody else. They've deepfaked their appearance and they're faking somebody else. Right? But then this is a setting where it's interactive. So the person who is conducting the exam can issue challenges to make sure that the participant can prove their authenticity. Right? They can issue challenges, which is different from detection, mind you. Right? Detection is passive. Here I'm talking more like an active scheme where the imposter has to be on their toes in order to succeed. Right? So you flip the burden back on the imposter, and that is the idea behind challenge response. Right? So it's an intervention which degrades the environment and degrades deepfakes. Okay, so for example, a simple example is you're talking to somebody you don't believe that they exist or they are not real, or they are real but they're deepfaking somebody else. One question you can ask them to do is to perform a non-trivial action, right? Maybe move their head backwards and so on. And this turns out that it degrades deepfakes. Okay? As opposed to a passive challenge, you can also do passive challenges where you don't ask them to do anything, but you still manipulate the environment somehow. Right? Maybe you illuminate their face, right? And there's like a change in contrast, and that also degrades deepfakes. But yeah, so how do you make this work? Well, if you look at the deepfake pipeline, I won't talk too much about this, but think of several stages needed to deepfake somebody like Tom Cruise. We examined each stage of this pipeline and looked at the weak links, and then came up with a taxonomy of different physical actions which target certain parts of these pipelines. For example, head movements really mess up the face detector. All right, turns out that the detectors assume that your face is, it's a headshot which is frontal. If you change the angle of the face detectors don't work anymore. Right? So if you're using a face detector to build a deepfake, that's that kind of action can degrade. So I had a whole new data set for deepfakes research, responsibly constructed and interested in this area, you can play with it. I just want to quickly just show you some videos, right? So for example, if you can see any of this, nope, people can see this? Yeah, you can see it, right? So you can see now, bottom is basically a deepfake of the person on the left. And I don't know if you can click it on again. I don't know what I'm clicking. No idea.
Yeah.
Oh, here. Okay, good. So if I ask the person to move their head, so this is the real person on the left, on the top, and they're trying to mimic the appearance of this person here. So if I ask this person to move their head to the left, you can see that there are noticeable, visible artifacts to deepfake pipelines, right? Or similarly, if I ask them, maybe I think that they're faking somebody else's appearance, I ask them to cover half of the face, and you can see that, again, visible artifacts can show up here. So this kind of active intervention is like a captcha that you provide to the participant. And if the participant is faking their appearance, this kind of challenge can break it. So you can build detectors around this. And I won't talk too much more except to say that this idea also works for audio, right? So I'm talking to a mic, but if I ask to cover my mouth, deepfake, voice deepfakes are degraded by these kinds of operations. So simple interventions can dramatically boost detection performance for these kinds of models. And this work has received a little bit of media attention as well. Okay, I think I'll wind up. To summarize, urgent need to separate true content from fake content. And I talked about a couple of different approaches to do this. Wind and seal are watermarking approaches, and these leverage the intrinsic properties of diffusion models, because that's not the end of the story, and there are other kinds of challenges arise, and our challenge response systems leverage the limitations of real-time adaptation. I'll stop here.
Okay. Thanks so much for the talk. Any questions from the audience? If not right now, then.
May I ask a small question?
Oh, yeah.
Yep.
Over Zoom,
Professor.
yes.
Yeah. Hi, Professor. Thanks for that talk. This question is about the first watermarking approach that you described. Essentially, like you add a two-step noise. First, you generate G, and then generate I. Can you give some intuition about this intentional? And there was also an M term, like a modulus M term. What is that?
Sure. Thank you. I sort of hand waved my way through a few details. I'm going to pull that up. Okay, here is, I think, what you're referring to. So this scheme here is our scheme. I think you're asking, why do we have this funny way of generating the noise, right?
Yeah.
I think that's the intent of the question. Okay, so a couple of reasons for that. So one is, I talked about this tension between verification and forgery, right? So we want to, so for this kind of watermarking scheme to succeed, we want two things. So one, we want a sufficiently diverse number of keys, because notice that these are not truly random keys, these are pseudo-random, right? So in order to match a particular output, there are only so many keys that you can generate. Otherwise, you get something completely different, right? So you want a sufficiently diverse number of keys, but also sufficiently small such that you can verify. Because if you have an exponential number of potential keys, then verification is very hard, all right? So how do we resolve this tension between diversity and verification? And that is where this two-step generation procedure helps, right? So we can think of this two-step procedure as basically amplifying the randomness using a smaller number of secret keys. So what we so that's the high-level intent of this sort of two-stage scheme. So in detail, what we do is we first sample uniformly an index ranging from 1 through n, and think of n as some moderate size integer, okay? And then so that will basically, and then do a percent m, which is a modulo operation to get like a cyclic salt, and use that cyclic salt for the pseudorandom number generator. So this kind of two-stage scheme is common in randomness amplification problems. And this enables us to achieve our robustness guarantee for forgery, which is that this two-stage process makes it impossible for the adversary. This hashing scheme that we used makes it impossible for the adversary to recover the salt. Hopefully that gives some sense of why we do this.
Yeah. Thanks a lot.
Yeah. I guess. Oh, there's another question.
All these methods we are tested on the pixel level. It tends to see a space on. And recently there's a new trend where it's to AI and ask it to generate the exact same image. That would mean in most of the scenarios, these watermarks might be lost because it again generates stars from a and it that's with its own. How can it happen?
Yeah. So the generative model that you just described is slightly different from the generative model that these watermarking methods are designed for. Yeah, you're right. If there is a noise input for that model, we could apply similar techniques. Like if noise is also an input to these models, and often that is the case because you want, common feature for these kind of generative models is creativity. So some element of stochasticity is injected into these generative processes to make the outputs look not monotone or typical, to get some more creativity into the outputs. So noise is often added at some stage or the other for these kinds of processes. So if noise is added, then one could apply these techniques. Yeah.
But that would mean the original watermarking was lost and this was like different watermark.
Right. Yeah.
So I guess one question I have with this is if you use the two different, does this watermark the output of a particular generative model, or is it so? Can you use the same watermarking technique? If I ran it with my model, would it still pass your verifier?
No. So in fact, this verification procedure is white box.
Okay.
So if maybe I'll bring it up. Either let's see. So notice that there's an inverse diffusion process for estimating the noise vectors.
Yeah.
And the inverse diffusion process requires you to know the weights of your model.
Mm.
So in that sense, the verification is white box.
Okay.
Yeah.
But
So,
what about the wind one?
Wind is the same thing. Yeah.
The same
so
thing.
we
Okay.
do inverse diffusion to reconstruct the noise and then verify.
Okay.
So that requires. So this is use case is most salient when you're trying to prove. Let's say that OpenAI is trying to prove that the image is actually OpenAI
Okay.
generated. Then they have access to their model weights and they can do this inverse diffusion.
I see. Yeah. And you could think of another way of watermarking where you want like anybody in the public should be able to verify that an image is AI generated. Is there are those?
Good question.
Is that a different problem entirely?
It's a very good question. Yeah. Again, I guess there's a axis of how you can characterize watermarking methods. So there are private methods, private key methods as public key methods. I'm using these terms loosely.
Okay.
But this is an example of a private key method, right? Where not everybody can verify.
Okay.
Right. It's not that anybody who has access to the image can verify whether it's been watermarked or not. The simple watermarks that we showed earlier, which is like you have text written in big bold letters, are public key methods. Anybody who looks at the image can verify it's been watermarked.
Okay.
Right. So this is the latter.
Yeah. Maybe there's those are more distortive. So maybe there's an axis of like how much public verification you can get with how much distortion.
Right. There are trade-offs there. So normally At least for commercial watermarks nowadays, at least, Google has something called Synth ID, which
Yeah, that's
it's
also
all
not public, right?
I'm sorry, it's all private key.
It's all private. Yeah. Okay. I guess one last question. A little more big picture. You're also from signal processing background or electrical engineering background. What ideas from signal processing do you think are, first of all, do you use now in machine learning, and also what do you think is going to be relevant in the in this era of generative AI?
That's an interesting, I guess, high-level question, right?
Yeah.
Stepping
Yeah.
level higher,
Not
beyond watermarking. So
yeah.
I mean, look, to be honest, I find the distinction very blurry.
Hmm.
When we talk about AI,
Yeah.
right? I mean, typically these are neural networks. Think your architecture, convolution networks, transformers, but convolution is sitting right there, right? Like there's like a basic signal processing construct underlying all of pretty much all of modern machine learning, I would say.
Yeah.
Transformers, but transformers is nothing but I would, in putting on my signal processing hat, I would call it a shift varying filter.
Yeah.
Right. So many of these building blocks are all, I would say, grounded in signal processing. So I don't. And where would we use signal processing tools? We use it all the time, right? Like we don't just think of it as.
I guess we're sort of moving up the tree of abstraction, where originally signal processing methods were developed for audio images. You're working at pixel level or the raw audio level, and now you're able to, with neural networks and a lot more data, you're able to go up into more semantic understanding.
Yeah, progress has happened over a period of time.
Yeah.
Right? And I mean, these architectures didn't come out of nowhere, right? Like somebody designed them, right? And there are inductive biases in these architectures, and these biases are all from signal processing, I would say.
Yeah.
Like it's very core to that. Yeah.
Thanks. Thanks everyone for it. Oh, is there one more question?
Is there any way to create the watermark on audios and other kind of generated?
Can we do similar things for?
Any research going on?
Okay, very good. So, so a lot of research going on, and I think this is a very salient problem as of today. Specifically to images, right? Everything I discussed today was for diffusion models, right? Like where I mean, it is specific to diffusion models. For audio and for text, different modalities. The generative process is not diffusion based. It's usually autoregressive transformer, decoder only transformer. There, similar techniques do not apply. So we are actively looking into extending or building analogs of these methods for decoder only models, but there are fundamental engineering challenges there. So I think I would just say great question and lots of open problems there.
Thanks everyone.